called damped oscillations, for example. What does the word damping mean to you in English?
Damp. To like soften.
Yeah, like a damped sound, right? So damping basically is to cause the system to lose energy, right?
Yeah.
So damping, by definition, is the decrease in amplitude, right? So we're saying that your maximum displacement is getting smaller and smaller, right?
Yes.
Max decrease in amplitude or energy, even more important. Maybe think of it as a decrease in energy, right? A decrease in energy. So it is more important. So think of it as a decrease in energy of an oscillating system. So it's kind of like your spring due to resistive forces. Resistive forces. Does it make sense to you? So kind of like your spring. In what context? So for example, if I start oscillating a spring, will it oscillate forever?
No.
Because,
over time it'll lose energy.
Correct.
Yeah.
Because of the damping forces. So maybe things like friction, isn't it?
Yes.
Will cause it. So friction is a damping force, isn't it? Will cause it to lose energy. So damping is the decrease in the energy of an oscillating system due to resistive forces. Okay.
Of
decrease in the energy of an oscillating system due to resistive forces.
oscillating is such a hard word to spell.
Is it a long word to spell? Right. Now, I want you to imagine something. And let's get into the word resonance first. But before you get what resonance is, I want us to think about what I mean. I want you to imagine, for example, I connect a vibrator. I connect a what?
Vibrator.
I connect it to a spring. I connect it to a what?
Spring.
A spring. And the spring in itself has a sort of natural frequency. It has a what?
Natural frequency.
What does that mean? Okay, so imagine the spring with no vibrator. First, the spring with no
vibrator.
Assuming the vibrator, for example, does not exist. Let's remove the vibrator. Right, so we're going to imagine a spring, no vibrator. If I was to pull the spring, extend it a bit, and then let it oscillate up and down, oscillate up and down, that is its natural frequency. It's the frequency with which it would vibrate, assuming there are no external forces. Except for the only force that's acting on it is the restorative force.
Restorative force?
Yeah, it's this force that after you pull it, you want to put it back.
Oh, yes.
It's the force that keeps it up and down.
Yeah.
When you pull the spring a little bit, you create a force. That force that's pulling the spring back to its sort of rest position.
Yeah.
It's called the restorative force. So if the only force acting on it is the restorative force, the frequency with which the spring would up and down is known as the natural frequency. Right?
Okay.
Good. So let's assume, for example, natural frequency, let's say is 50 hertz. It's 50
hertz
as an example. I then connect the vibrator. Right? I connect the
vibrator.
This time, the vibrator, which is on the wall, is forcing the spring to vibrate. It's doing what?
Forcing the spring to vibrate.
Right. So say, for example, the vibrator starts off at 10 hertz. What is the natural, and let's say our spring has an amplitude of 3 centimeters, right? It's up and down by
3 centimeters.
That's the maximum amplitude.
Yeah.
I increase the vibrator to 20 hertz. What do you think happens to the amplitude?
It'll
increase from 3 to maybe 5 centimeters.
Yeah.
Right? Maximum and minimum becomes 5 centimeters. And then what happens when I get to 30 hertz from the vibrator? This might then increase even further. From 5 centimeters, my maximum maybe becomes 7 centimeters. And the amplitude also say 7 centimeters. Makes sense, going up and down by an amplitude of 7. And what did I say the natural frequency was? 50. If I then increase the vibrator to 50 hertz, this amplitude could then extend to even as much as, let's say, 10 centimeters. It vibrates up and down by how much?
10 centimeters.
10 centimeters.
Yes.
What do you think happens if I exceed 50 hertz now? I go beyond 50 hertz. Because 50 hertz is the natural, so the vibrator is set to the natural frequency. The vibrator is set to the natural frequency. Now they're together, right? They're similar. They're exactly the same. What happens if I exceed 50? What if I go to 60 hertz now?
The spring
Would increase beyond 10 centimeters?
No.
It will decrease.
It will decrease.
Instead of 10, it might go back to 7.
Oh, wow. Okay.
And if I increase further, let's say I go to 70 hertz, where there was 7, it might even be 3.
Okay.
Do you see what's happening?
Yeah.
That you only get the maximum amplitude when the forced vibration is equal to the
Natural frequency.
Anything below that or above that will result in less amplitude.
Yes.
Less what? Less vibration.
Yes.
Is that making sense?
Yeah. Okay, so
resonance.
resonance.
The definition. When we get resonance applies means maximum vibration. When do we get that?
When the vibrator's vibrating at the spring's natural frequency.
Correct. So resonance is the point
Resonance.
at which the oscillation is at max displacement or max amplitude. So the oscillation is at max amplitude. Well, what has happened for that to happen? When forced or driving frequency, forced frequency or driving frequency or forced frequency is equal to the natural frequency. Okay? When the driving frequency or forced frequency is equal to the natural frequency. And at that point you have maximum amplitude. That is resonance.
It happens when the force
Or driving frequency is equal to the natural frequency. When the driving frequency is equal to the
natural
frequency. When the driving frequency is equal to the
natural
frequency. See, right?
Okay.
So in this case, what does the graph look like? If this is the amplitude, let's say we were increasing from 0 to 10 to 20 to 30 to 40 to 50, right? And then we went going 60, then 70 hertz, right? Remember, as an example. And here's the amplitude in centimeters in our case, right? Should be in meters really. But the graph is an issue like that. And then when was it natural? At 50, right? So at 50 we got to maximum. And then beyond 50, what happens to the amplitude? It starts to
come back down again.
Decrease.
So is it supposed to be a straight line, or is
no, it's a curve.
There's a bit of a curve there. Okay.
It's a bit of a curve, and like that. Okay, does it make sense?
So it's amplitude against frequency.
Amplitude against frequency, or displacement against frequency. Does that make sense? Let's say, for example, on this spring, our spring there, right? On our spring at the top in the diagram, let's say, for example, we attached a piece of paper there. We attached a
piece of paper.
So it's still connected to the vibrator, but maybe we attach a small piece of paper. Would that affect the damping?
A small piece of paper.
attached to the mass.
Yes.
Yes, because maybe it's catching more wind, isn't it?
Yes.
As an example, right? If you add damping, you then achieve resonance sooner. If you add damping, you will achieve resonance
Sooner.
at a lower frequency. Does it make sense? So the graph will look something like that. And if you add more damping, it will happen even sooner. Does that make sense? Like that. So the point of resonance is reached sooner, and of course the amplitude of that resonance is even smaller. Does that make sense, right? So this is with damping applied. With damping applied, maybe like a piece of paper put on there. Is that making sense?
Yes.
Okay. So what happens when you put a piece of paper?
When you put a piece of paper, it increases the damping.
It increases the damping, but what happens to the frequency at which damping is at which resonance is
It
achieved?
decreases.
Correct. And also what happens to that maximum amplitude?
It decreases.
Also decreases. All right. Do you get that?
Yes.
Right. Good. Maybe your amplitude should actually be at 0 here, hey? This amplitude should be at
0.
0 now. So give it another, then that's like that. Okay?
Okay.
Alright. I hope that makes sense. Now, there are 3 types of damping. Shall we discuss them? There are 3 types of damping. There is what we call light damping. Right? All of these result in a change in a loss of energy, right? But in light damping, so for example, this is your maximum displacement, and this is time. Light damping will look something like this. But you'll notice something. What's happening to the energy, to the amplitude?
It's decreasing over time.
Good. The amplitude is decreasing, but the period should remain constant. So this is 0, for example. This is one wavelength is here, right?
Yeah.
This is one wavelength here. So maybe this might be 2 seconds, which means that another one wavelength will be at
4 seconds.
Does that make sense, right?
Yeah.
So the period never changes. Note that. Damping does not affect period.
Sorry, what is light damping?
Oh, that's a good question. Damping does not affect period. But let me answer that question now. Does not affect.
So is this for all kinds of damping or just light damping?
You'll understand what I mean just now. So light damping means that you generally have more than one oscillation.
Okay.
So in light damping, you have more than one oscillation. Like in this case, we have 2 and a bit, isn't it?
Yes.
You have more than one oscillation. If that makes sense, right? You have more than one oscillation. Have you seen like those cowboy doors? The cowboy walks through the door, or I don't know, like the Jesse Jones, I don't know, walks to the door, and then they kind of
The doors flap,
flap back and forth several times,
Yes,
right?
yeah.
That's light damping,
Okay.
right? Eventually they'll stop, but
Yes,
they'll
yeah.
go back and forth several times, right? Now, let's discuss what is known as critical damping. Critical damping. In critical damping, this is still displacement.
So the graphs, they vary. So this graph is only for light damping.
Which one?
This one.
This is light damping.
Okay.
Now for critical damping, where this is still displacement, it's the shortest time for it to come to rest. Right? So in critical damping, it represents it's damped, but it still comes to rest. Are you with me?
Yes.
But it's if it happens within the shortest time for which to achieve this, we call this critical damping. All right. So in critical damping, we're referring to the shortest time for the object, the oscillating object, to come to rest. Okay, that's critical damping. Shortest time for the object to come to rest. And notice you don't have a single oscillation, right? As soon as it comes to rest, it stops. An example of this, like, is maybe like your car shock absorbers. Car shock absorbers, right? In your car shock absorbers, we don't want you to bong 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 for a pump.
Yeah.
Is that making sense, right?
Yes.
You want to come to rest. As soon as you hit a hump, you want to come to rest.
So sorry, it's amplitude against time.
Yes, displacement against time, or amplitude. Yeah. Well,
So-
plus maximum displacement, so it's displacement against time.
And it's a curve, right? Not a
It's a
straight.
curve, yeah, it's a curve. Kind of like that. So you notice with critical damping, not even a single oscillation. Light damping, you'll have more than one oscillation.
So to
It's the shortest time
the shortest time.
for the object to come to rest. That's critical damping, right?
Yes.
And then there is what we call heavy damping. Heavy damping. In which case, this is X against T. Heavy damping now it still doesn't make a single oscillation. It doesn't make a single oscillation, but it takes a bit longer. Does it make sense, right?
Mm-hmm.
Right. So not a single oscillation again. Not a single oscillation happens. You understand what I'm saying, right?
Yes. Yeah.
But the object takes or the object returns to equilibrium very, very slowly. Does that make sense, right?
Yes.
Can you think of an example of this? Where something like just takes forever to rest to oscillation.
Yes, that is a bit of a tough one.
An example of this is, do you ever open those hotel doors?
Yes, and then they take so long to close.
You can't even
behind
force it to close.
Yes, exactly.
You know what I mean, right?
Yeah.
Those hotel doors, you can't even force them to close, and they sort of slow. Well, maybe to protect you from hurting yourself, isn't it?
Yeah.
So you force it open, and it's kind of just really slowly closes.
Yeah.
Does it make sense, right? Again, not a single oscillation. You appreciate that, right?
Mm-hmm.
And it returns to equilibrium position very, very slowly. Okay? Make sense?
Yes, it returns to equilibrium position really, really slowly.
Very, very slowly, yes. Okay.